Well, presenting next is Wai Hei Ngan, who is a Ph.D. candidate at the University of California, Davis. Race Talk asks the question, is machine learning-based browser fingerprinting detection robust to obfuscation? Ray, thanks so much for being here today. I will hand it over to you.
Thank you, Paul. So today I'm going to talk about investigating robustness of browser fingerprinting detectors. My name is Wai Hei. I'm an undergraduate from UC Davis, as well as a researcher. So first, why do we want to know if machine learning-based browser fingerprinting detection is robust to obfuscation? Researchers are building machine learning-based detection approach to detect various types of tracking behaviors, including browser fingerprinting. Second, the focus on prior research is on evaluating accuracy but not on the robustness against adversarial tactics that's commonly used in the ad blocking arms race. So what is browser fingerprinting? A browser fingerprint is information collected about a remote computing device for the purpose of identification. Fingerprinting scripts combine data from both hardware and software to create a unique identification, just like a fingerprint. A fingerprint identification can be generated based on its platform, plugins, time zone, and etc. Once you're ID'd, you'll be tracked across multiple sites, and details about your life can be compiled into a profile. This is also called cross-site tracking. While fingerprinting is a relatively new concept, you might be more familiar with tracking cookies, which are also be able to follow you around the web. They act similarly in terms of their purpose. However, one major difference is that browser cookies are stateful, therefore it's trivial to block, whereas a browser fingerprinting is stateless, thus it's not trivial to detect a block. So this brings us to FP Inspector. FP Inspector is a state-of-the-art machine learning approach that addresses accuracy and coverage issues in fingerprinting detection. FP Inspector uses static and dynamic analysis to capture the script's behavior. Then it uses that representation to train machine learning models that are used to automatically detect browser fingerprinting scripts. In static analysis, the script is represented as abstract syntax tree, which normalize the script and allow extraction of API usage. Dynamic analysis uses JavaScript execution to capture the API calling frequency and the higher level semantics. Static analysis helps FP Inspector overcome the coverage issues, and dynamic analysis is mainly used to handle obfuscation. So the prior research evaluated the FP Inspector accuracy to 99.9%. However, it did not test its robustness against obfuscation, which is an adversarial tactic that is commonly used in the ad blocking arms race. We want to investigate how well FP Inspector does against obfuscated scripts, and if that accuracy of 99.9% still remains the same. So here's my research approach on FP Inspector against obfuscation. We first obfuscate script using various publicly available code obfuscator, such as build-file tools, Google Closure Compiler, Draft Logic, JFox, and Office.io. Then we put FP Inspector to test against both obfuscated and non-obfuscated script. We then use the confusion matrix to visualize the performance of the classification model. Correctly identified fingerprinting script is classified as true positive. Correctly identified non-fingerprinting script is classified as true negative. Incorrect classified non-fingerprinting script is classified as false positive. And lastly, incorrectly classified fingerprinting script is classified as false negatives. So here's the accuracy percentage of dynamic and static analysis with each obfuscators. We can see that FP Inspector did pretty well overall. Most obfuscators have a percentage of 99%. The only two exceptions are for build-file tools and draft logic in static analysis. Let's see if this error is caused by false positive or false negative. In here, we can see that the false negative rate for build-file tools and draft logic is 100%. meaning that all fingerprinting scripts identified in the control group were misclassified after they were obfuscated. In dynamic analysis, however, it was able to handle the build-file tools and draft logic obfuscation with much success. We can see the decrease of accuracy of build-file tools and draft logic is caused by false negatives. In the false negative graph representation, we can see the actual number of scripts for each obfuscator in both dynamic and static analysis. Here, we can see a better visualization of how dynamic analysis performs better than static analysis. Also, how build-file tools and draft logic compare to others in static analysis. Both build-file tools and draft logic uses eval obfuscator. The eval function evaluates JavaScript code represented as a string, and is generally not recommended to be used as a good coding practice, since it might contain malicious code and it executes terribly slow. With the same script URL, we can once again see that the static analysis did way worse than dynamic analysis in the false negative dataset, proving that the dynamic analysis is better than static analysis in identifying obfuscated scripts. So here's my conclusion for my research. First, the obfuscator that introduced a high false negative both uses eval obfuscation. Second, we can see that dynamic analysis performed better than static analysis overall in analyzing obfuscated scripts. Specifically, there were more false negative in static analysis than dynamic analysis. Third, we know that the obfuscation indeed hurts accuracy of either dynamic analysis or static analysis. However, since FE Inspector uses an OR logic of both analysis, meaning that if either dynamic or static analysis detects a script to be fingerprinting, then it would be classified as fingerprinting. This is a surprisingly good approach even when the scripts are obfuscated, since we can see that there were very few false positives and there are a lot more false negatives. This approach will be able to overcome the high rate of false negative that is caused by the static analysis. Therefore, we can say the accuracy of 99.9% of FE Inspector still remains even when the scripts are obfuscated. That's it. Thank you.
Well, thanks so much, Ray. Let's take a look at a couple of questions that we've gotten in while you were speaking. Both of them have to do with dynamic analysis. It seems pretty clear from your presentation that dynamic analysis is outperforming static analysis. One question that we've had is, are there any limitations to dynamic analysis when using this approach?
So for dynamic analysis, like that I know of, like there's no any limitations. The only limitation for my research is that some of the script won't be able to obfuscate, and some of the script won't be able to replace to activate that dynamic analysis like approach. Since dynamic analysis uses like JavaScript calling frequency, so it's harder for that to work in my research. But then in the wild, it works properly. So yeah.
Yeah, and in the same vein, we've got another question that's come in asking if there are any advantages to combining both static and dynamic analyses, or is the future only going to be in a dynamic approach?
So yeah, there is a benefit of combining both static and dynamic, since like there weren't like a lot of false positive. Like there are a lot more false negative that was caused by static analysis, specifically towards like obfuscation. So combining them is actually good for us. But then in the future, if there's an obfuscation techniques where it introduces a lot of false positive, then it might not be as a good approach to combine both of them. Since like if either one is classified as positive, then it would just be classified as positive. So yeah.
Perfect. Well, Ray, thanks for making some time for the summit today and for answering some of our questions. We really appreciate it.
Thank you, Paul.